everyone. Welcome back to the lectures on Introduction to Multi-Agent Systems. In the previous lectures, we studied the distributed averaging models, and we realized that some of the nodes seem to be more important than the other nodes. Just for an example, if we have a network where there are certain globally reachable nodes, then we know that the final states of the rest of the agents in the network are actually driven by the initial conditions of these globally reachable nodes. Now the question is, we understood that these globally reachable nodes are important. But how do we quantify their importance? This leads us to the notion of centrality measures. But before we exactly define what a centrality measure is, first, let us try to define what do we mean by the notion of importance in a distributed system. And we begin with a distributed system, which is well known to us, which is the distributed averaging system. So let's get started. Consider the network shown in this figure. The set of agents which are shown here, let us say that they follow the distributed averaging model. Under the distributed averaging model, we already know that the subgraph of nodes shown here are globally reachable and aperiodic. Globally reachable implies strongly connectedness, and it's also aperiodic, meaning the corresponding adjacency will be primitive. We already know that under the distributed averaging model, the states of all of the agents are driven towards the states of agents 2, 3, and 4. So in some ways, these three nodes are actually or act as leader nodes or in some ways central nodes. So can we exactly say that in any general network, what are the nodes that play a key role in deciding the emergent behaviors in the system? Let's write it. Any given arbitrary network, directed or undirected, which are the nodes that play a key role in dictating or deciding the emergent behaviors of the overall system. Are they always the sinks in the network? Sinks not in the network, but sinks in the condensation graph. Notice that all of the nodes shown here are actually sinks. If this network is denoted as G, these are sinks of the condensation graph CG. Sinks of CG always drive the overall output of the system in the case of a distributed averaging model. However, can we generalize that statement? Can we say that such nodes always play a part? Or sometimes some topologically or locally important nodes play a part. Like maybe some nodes have a lot of neighbors to begin with. Let's call them in some ways locally important nodes. Can they play a key role in some cases? Well, for some measures, they also, for some applications, locally important nodes play a part in determining, or locally important nodes become, in some ways, the central nodes. Or sometimes these are such nodes that always appear in every path that we take in the network, meaning pathwise important nodes. The important thing is any of these factors can actually decide whether a node is central or not. Why? Because which node becomes central depends a lot on the application that we are looking at. Let's write it. This is a very important idea. Which node acts as a central node depends heavily on the given application that we're trying to solve. Or scenario. With this, let us try to formally define what exactly is. Let's write it. In order to actually dig out which nodes are central, we'll have to first define a measure with which we say whether the node is central or not. Such a measure is known as a centrality measure. So let's define what's a centrality measure. A centrality measure, or score, assigns a value or a score to every node in the network based on its relative importance within the network. In other words, simply provides a ranking of all the nodes in the network. A ranking of the nodes. So what are the different centrality measures that are available to us? Let's start with the most easy to understand centrality notion, which is that of the degree centrality. So what is degree centrality? Degree centrality is extremely intuitive and, as I said, very easy to understand. For any up for any or for an arbitrary digraph G, degree centrality of, say, a node I of node I is defined as or denoted as C degree I, where C stands for centrality and the subscript degree here tells us that we are looking at the centrality in terms of the degrees of the nodes. Okay. Is simply equal to its in degree. C degree I of a node is equal to the summation is equal to, let's write it first, din of I and is equal to summation of a ji, the summation of all of the ji's where j goes from 1 to n. This is known as degree centrality. So why are we looking at the in degrees here? Just a quick reminder. Again, let's go back to the example which we saw here. Notice that only the globally reachable nodes to which every node either has a direct path or either has a direct edge or a path via some other nodes. So basically, in degree is what tells us who is affecting whom. Like if we draw an edge like this, Ji, then we know that I affects J, which is why in degree counts. So please pause the video here and try to think where exactly can degree centrality be important, where it is important to have a lot of neighbors. There are many examples. Let's say in the academic or scientific community, one example would be, let's write it. Degree centrality is widely used in citation networks. What is a citation network? It simply tells us who cites whom. And based on that, we can create a graph. Obviously, this graph is directed because if one paper cites another paper, it's not mandatory for that other paper to also cite the first one. So that's why these graphs are obviously directed in nature. So what does degree centrality do in the citation networks? It is used to generate a ranking of the papers. Ranking of scientific articles. Obviously, this is very relevant and intuitive because if the paper is highly cited, then a lot of people trust it more. And hence, it makes sense that such a paper would have a very high rank. Although such a measure may or may not be an accurate description of which is the best paper of all the papers that are there. Just a word of caution. Is there any other example where degree centrality is used? The answer is yes. Influencers in social networks have relatively high in degrees. in degrees, hence implies they tend to be ranked well as per the degree centrality. Okay, similar to the in degree centrality, we can also define an out degree centrality. In some motions, out degree can also be important. Let's quickly see first how would we define an out degree centrality. Right. Similar to in degree centrality. We also have yet a centrality measure in terms of out degrees of the nodes. Two, obviously, as out degree centrality. And degree centrality given by C superscript 0 subscript degree of I is equal to its out degree, which is simply equal to the summation of A ij's. J varies from 1 to n. What does an out degree signify? Let's see. Having a high out degree simply means that we are talking to more number of people, meaning it can sometimes reveal information about traits of the individual. In other words, we can say that if the network represents a communication network, let's say like a social network, like LinkedIn, Instagram, or Facebook, between of a group of individuals. Let's write it. Let the network represent. In that case, very important point, a high value of or a high score of in degree centrality, score from in degree centrality, implies popularity, meaning more and more people follow this particular individual. On the other hand, a high score from out degree centrality. Reveals that the person is very friendly and can make a lot of neighbors or friends. Or in other words, we can say a high score from out degree centrality implies gregariousness. Of the individual. So these are the important definitions pertaining to degree centrality. Let's see a couple of quick examples which will solidify our understanding of these notions. So, page. Let us look at the digraph shown in this figure. Let's try to write out the in degrees of all of the nodes, which is directly equal to the in degree centrality scores, meaning the in degree or the degree centrality score of node number 1 is simply equal to the number of neighbors it has. So please note that if the graph is undirected, then out degree and in degree centrality scores are the same and simply represents the number of neighbors they have. So node number 1 here has a score of 1. C degree of node number 2, as we can see here, it has 3 neighbors, so this is equal to 3. The score for node number 3 is equal to 2. The score for node number 4, let's do something. Let's just it'll just help us write it faster. 5 and 6. Okay. The in degree score of node number 4 is again equal to 3. And the in degree score of node number 5 is again equal to 3. And the in degree score of 6 is equal to 2, given by these two edges, these edges. So which nodes turn out to be the central nodes here? The highest scores are associated with nodes 2, node number 2, node number 4, and node number 5. If you want to mark them here, it would be node number 2, node number 4, and also node number 5. These 3 nodes are the central nodes in the network. So this was the example of an undirected network. We can also do this exercise for a directed network. Let's try to do the same exercise of calculating the degree centrality measures for the directed network that is shown here. Let's look at node number 1. Notice that node number 1 does not have any in neighbors, meaning its degree centrality score is simply equal to 0. Node number 2 has 1 in neighbor, meaning its score is 1. For node number 3, again, there's just 1 neighbor in neighbor. Node number 4 again has just 1 in neighbor. Node number 5, if we see, has 3 in neighbors. 1, 2, and 3. Meaning its score here is equal to 3. So according to popularity, which node would become the most popular node? Obviously, the score is highest for node number 5. Meaning here, node number 5 is the most popular node. But is this again the most gregarious node? In order to answer that, we'll try to calculate the centrality now in terms of the out degrees. So let's do that. It's the same diagraph that we have, and here the centrality of node 1 is equal to 1, and node 2 has 2 out neighbors, so this is 2, and node 4 has 2 out neighbors, and node 4 has 2, node 3 has just 1, and notice here the most popular or influential node is actually the least gregarious node. Its ranking is the least in terms of its gregariousness. So while it is very influential, it does not receive information from a lot of neighbors. And in this case, out degree centrality wise, central nodes are actually node number 2 and node number 4. They have an equal out degree equal to 2, given by this. The applications that we discussed here in this context of, let's say, communication networks, the notions of in degree and out degree centralities reveal very relevant information. However, let us go back once again to this example. The undirected network that we analyzed for the case of, again, the undirected case that we looked at. Okay, if we observe here, nodes number 2, 4, and 5 turn out to be the most central nodes. However, let us zoom in a little bit more. What we can observe here is that, let's copy this diagram and let us write some very important observations. So now we are trying to decide whether we should pause at the centrality measure, or are there any flaws in the centrality measure which would perhaps motivate us to look for other measures. Let's try to analyze that. What we can observe here is that nodes 2, 4, and 5 are central, are equally central, in fact. But are they really equal in every sense of the way? Let's analyze. What are the neighbors of node number 2? The neighbors are 1, 3, and 4. Of the neighbors, we see that 4 again has a very high centrality score, but 1 and 2 are not central in terms of their degrees. Okay, again, node number 4, its neighbors are 2, 5, and 6. There are 2 central neighbors, which are its neighbors. Similarly, for node number 5, the neighbors are 3, 4, and 6. The central, only one of the nodes, one of the neighbors here is central, that's node number 4. So what do we observe? We observe that node 2 has just one neighbor which has a lot of importance. Similarly, node number 5 has just one important neighbor. However, node number 4 has 2 important neighbors, node number 2 and node number 5. So in some ways, it seems like there should be a measure that should be able to convey this information, that not only Does 4 have a lot of neighbors? It also has a lot of important neighbors, meaning in some ways it seems to be more central than nodes 2 and 5. So, is there really a centrality measure which can give this information? This is exactly what we will discuss in the next lecture. So, I'll pause here right now. Um, I'll suggest the students to think by themselves if they can arrive at any centrality measure which can somehow now make 4 as the most central node. Thank you.